In this last video on the pre-calculus algebra topic of rational functions and their graphs, we'll graph one more rational function and then solve a average cost function application problem. To start with, let's look at this function. Oh, I'm seeing now that it's going off the screen. Let me see if I can fix that. There we have it. So we have a graph f of x equals the opposite of 1 over x squared minus 4. And let's just walk right through the different steps. I've started some of those steps here to keep the video a little bit shorter, but when we start off, the first step is to evaluate if it's even or odd. The reason we're doing that is because if we can find some symmetry, then that symmetry is going to make graphing the function much easier. So when we evaluate f of the opposite of x, we can determine whether it's even or odd. To do that, I'm going to simply replace all the x's with the opposite of x. And look at what happens in this case. When we replace x with the opposite of x, we get f of x back. So what that tells us is that this function is even, and therefore it has y-axis symmetry. Next up, we can find the y-intercept. The y-intercept is found by letting x equal 0. And when x equals 0, we have the opposite of 1 over 0 squared minus 4. So that's the opposite of 1 over negative 4, which is 1/4. So we have this y-intercept 0, 1/4. Next, moving on to step 3, we're going to look for the x-intercept, and we find the x-intercept by letting f of x equal 0. Or in other words, when is this negative 1 over x squared minus 4 equal to 0? Well, do you remember that to do that, we just take the numerator? So we let 0 equal that numerator, negative 1. When 0 equals 1 or negative 1, we would have x-intercept. But 0 is never negative 1. It never occurs. So what we can say here is that there's no x-intercept. That tells us, it gives us a little bit of a hint about some asymptotes, doesn't it? But let's keep going and look for those asymptotes. To find the vertical asymptotes, we're going to set the denominator, the x squared minus 4, to 0. So we're going to find when is the denominator 0. The denominator is 0 when x is 2 or negative 2. I'm getting that by factoring this difference of squares. X squared minus 4 is equivalent to x minus 2 times x plus 2, and that gives us x is equal to 2 or negative 2. So those are our two asymptotes, vertical asymptotes. Now we'll move on to horizontal asymptotes. That's where we divide the top, the 1, divided by x squared. And you can see that this 1, the degree of the 1 is a 0. And that 0 degree, a degree that's smaller than 2, is too small to divide by x squared. So this bigger degree of 2 cannot go into the degree of 0 at all. So we'd say that the asymptote is 0. We have y equals 0. Not because this degree is 0. It's let me give you another example. If anytime it comes down to anytime that the numerator has a smaller degree than the denominator. So if I were dividing an x divided by x to the 5th, this degree of 1 is smaller than the degree of 5. So we'd have an asymptote of 0, and so on. Anytime the degree of the numerator is higher than, or I'm sorry, lower than the degree of the denominator, so the degree that we're dividing into is too small, we'd say that the asymptote is 0. Y equals 0. So we've got 3 asymptotes running. And now for number 6, we can plot a few points. When I do f of 2, we already know that that's going to give us a 0 in the denominator because we knew that was an asymptote. But when x equals 2, y doesn't exist. And then we could calculate when x is 3 halves. That'd be negative 1 over 3 halves squared minus 4. So that's 9 fourths minus 16 fourths. Or in other words, negative 1 over negative 7 fourths, which is 1 over 7 fourths, which is the reciprocal of 7 fourths. So we'd get 4 sevenths. And continuing on, we could find when x equals 3, 4, or 5. We could find what the values of y are. I'm going to leave that to you to work out, but I'll tell you that we got, for x equals 3, we would get negative 1/5. For x equals 4, negative 1/12. When x equals 5, negative 1 over 21. So we can see it's getting smaller and smaller, right? Let's pull all this together to try the graph. I'm going to make this graph a little bit bigger so we can use it. And here we go. So we'd, applying all of this information, make note that we've got a y-axis symmetry. Oh, and by the way, that's why I didn't do any negative x's. Because what I know is that if let me actually fill it in here in the graph so you can see this. If I let x equal negative 1, y is going to be 1/3. If x equals negative 3 halves, y is going to be 4 sevenths. So we're symmetric across that axis. I don't have to find these negative x's in addition to the x's we've already found. Here's what the graph is going to start to look like. It's a little bit different than the other graphs we had. We could start by plotting these points that we've found, because that's going to help guide us. When x is 0, y is 1/4. When x is 1, y is 1/3, a little bit higher. When x is 1.5, we're going up to 4 sevenths, so still not at 1. And then we keep going, but then do you see how we're going to start climbing? As we get closer and closer to 2, we're going to get closer and closer to that asymptote. And then when we jump over to x equals 3, we're down here at negative 1/5. And when x is 4, we're getting smaller and smaller, so closer and closer to the axis. It's hard to tell what's happening here until I keep going. But I could put the points across the axis on here, so I could see this, and so negative 3, negative 1/5, and so on. And let's keep going, because this looks a little confusing so far, but you've got to keep plugging away. We've got this point 0, 1/4, that's already on. We've got the no X-intercept, so we know we're never crossing that axis, but that's because we've got this y equals 0 is an asymptote. Let me graph that asymptote in here. And x equals 2 and negative 2. Can you start to see what's happening with this graph? What would happen if I found a point like 1.9? We'd start to see it better, but let me get another color ink in here. We're going to look kind of like a parabola here. So a U looks like this. And then on these other two asymptotes, we're getting closer and closer here. And as you might guess, that's what's going to happen over here also, is we're going to get closer and closer to the asymptote. So we get this graph. I know it's not easy to calculate that from the points alone. That's why we need these vertical and horizontal asymptotes to guide us also. But here's what the graph would look like. I know it might seem a little bit challenging to get that on your own, but if you practice enough examples, then eventually you'll get to where you can graph those with no problem also. And use those steps as your guide. Let's try an application that uses rational functions. It's the application of average cost function. So we've got the cost, C in dollars, of producing X mountain bikes is C of X equals 100,000 plus 100X. What this tells us is our fixed cost, the fixed cost is $100,000. So this company needed $100,000 to start. And then it costs $100 per bike. Each bike they manufacture is going to cost $100 more. So write the average cost function. What we do for the average cost function is we say, here's our cost, 100,000 plus 100x. There's our cost function. And then to do the average cost function, so we put a bar over that C, we divide by the number of x's. So here's our average cost function. And next we could interpret that cost in that function for the average cost of 1,000 bikes. 1,000 bikes would be, let me write the function again so we don't lose sight of that. It was 100,000 plus 100x all over x, right? So if we replace the x with 1,000, we'd have 100,000 plus 100 times 1,000 all over 1,000. So 200,000 divided by 1,000. We could do that without a calculator, right? Just dividing out powers of 10. So we'd get 200. What does that mean? It means that the average cost per bike, if they've manufactured 1,000 bikes, the average cost is $200 a bike. And then we could do the average cost of 4,000 bikes is going to be the fixed cost of 100,000 plus 4,000 times 100 all over the 4,000 bikes. So that gives us 500,000 divided by 4,000 divide by 1,000 to get 500 over 4. 500 divided by 4 is 125. So what does that tell us? The average cost per bike, if we manufactured 4,000 bikes, would be $125 per bike. So we can see that this company is making more and more money the more bikes. The price, their cost is getting smaller and smaller the more bikes they manufacture. What's the horizontal asymptote for this graph? If we have 100,000 plus 100x over x, the horizontal asymptote is when 0 equals, or let me work it out so that I can show you. So I can walk through the process. The horizontal asymptote, remember we divide, so 100x plus 100,000 divided by x. So off to the side I'm thinking, if I'm doing long division, 100x divided by x is 100. So we get y equals 100. What does that asymptote tell us? If you could picture the graph, if you could picture the average cost function and its graph, then you might see that when y is 100, when we have that asymptote of y is 100, the cost per mountain bike is approaching $100 as more and more mountain bikes are produced. So as we hit our point that we want to hit is getting to where the cost is $100 per bike. So after this company's been in business for a while and made many bikes, it's costing them about $100 per bike. But they're not there yet. They have a ways to go before they get there. Well, I hope that these examples have been helpful to you and that it's helped you understand some of the problems in the homework a little bit better. Please let me know if you have further questions about these, and we'll be working out some other examples in class as well.